All right, well, today I just wanted to first review some of the techniques that we had for common integrals that have trig functions in them. You'll see when we do the next section that those substitutions for the next section actually generate integrals of this form, and so these are useful both from applications and from other trig substitutions that we're going to get. What if I have an integral of cosine squared or of sine squared? What can I do to solve this thing? There's a common trick that people like to use, and it is to rewrite this just using the half angle identity we said, right? So this is just a review problem from last time. We can rewrite cosine squared as 1 plus cosine 2x all over 2, and each of these terms in here we can integrate. So I'll put equals dot, dot, dot. Similarly, if it's integral sine squared, we put 1 minus cosine 2x over 2, and we can do that one. That's a nice trick to remember so you can get those whenever they come up, and they're going to come up again today in some of the integrals that we do here, new integrals that we do here. How about if I have an integral of a power of sine times a power of cosine, where at least one of the powers is odd, right? The trick was if either power is odd, so for instance this one, we can substitute u equal the other trig function. So on this one, I'm going to substitute u equals sine x, since the power of cosine is odd. And I'll say if u equals sine x, then du equals derivative dx is cosine x dx. And by the way, these all work not just for cosine and sine of x. You can put kx in here, and it works just as well. So now on this one, if I make this substitution, then I first rewrite the integral pulling out what I need for dx, cosine x dx. Well, I'll write this as sine squared x times cosine squared x, cosine x dx. And let's see, I've got some background noise here. Maybe that'll take care of it. Okay. The cosine x dx then becomes du. Right? Sine squared becomes u squared. Still getting some noise. Hold on. Maybe that's got it. Okay. And then cosine squared, what do we do with that? We say cosine squared is 1 minus sine squared, which is 1 minus u squared. So what happens in these power of sine times power of cosine integrals is if at least one power is odd, 3/4 of the cases, right? You can rewrite this as an integral similar to this, u squared times 1 minus u squared du becomes an easy integral of polynomials. It always gives you a nice integral with powers of u instead. So here we've got u squared minus u to the 4th that we can integrate. And I'll just put equals dot, dot, dot. That one's easy, right? U cubed over 3 minus u to the 5th over 5, put back u equals cosine, sine x. Any questions on those? Does it look familiar? I hope. Those will come up a lot. And then finally, suppose I have to integrate a power of tangent times a power of secant. These will actually come up in some of our substitutions next section, as well as in some rare applications. How do I integrate this kind of a thing? And this one we said if the power of tangent is odd or the power of secant is even, we can make the substitution. So it's not like this where if they're both even, you say, well, I got to try another technique. If this one's odd or this one's even, well, this one's even, so let's try the substitution here. U equals the other trig function. U equals, since this one's even, I'll try u equals the other one, tangent x. Then du would be the derivative of tangent x dx. We were just doing this right at the end. Is secant squared x dx, right? Power of secant is odd, substitute u equals tangent. Excuse me, power of secant is even, substitute u equals tangent. And I have this substitution, and so now I rewrite tangent squared as u squared. Secant squared dx is now du, right? And this just becomes u cubed over 3 plus a constant. Becomes tangent cubed over 3 plus a constant, right? And if you have a higher power of secant, you can use the trig identity tangent squared plus 1 equals secant squared to rewrite this in terms of powers of u also. So there's a trick for a power of tangent times a power of secant example. That one look all right? Well, then finally, I want to finish up with one more of those that's very similar and say those are the first 3 cases. Case 4, then, is suppose I have an integral of a power of cotangent, and again, it can be kx, not just x, times the power of cosecant. These tend to come up together in certain applications. So how do I rewrite this one as something I can do? Because, right, that's nasty. And the idea is that if u substitution is obvious, an obvious thing to try if you see a function of a function, you try letting u be the inside function. But these kind of integrals, it's not always clear what the inside function is. And so you just memorize that if you see this kind of an integral, it's just like tangent to a power times secant to a power. If m is odd, substitute u equal cosecant, the other trig function. But if n is even, right, this one odd or this one even, let u equal the other trig function, cotangent. And then you have to calculate du to make the substitution, right? So there's this kind of integral. So suppose I had cotangent to the 6th, let's see. Let's do this one. Integral cotangent x over cosecant squared dx. How about that? Oh, this is, let's see, an odd power here, so I can substitute u equal cosecant, or an even power here, so I can substitute u equal cotangent. Which one should I substitute? And actually, one of the 2 is easier. They both work, but one is easier than the other. Well, let's see. I'm going to substitute u equals cosecant x then, I guess. Would be easier of these 2, and I'll show you why in just a second. But you can do either one and eventually be able to do it either way. If u equals cosecant, you remember the derivative of cosecant, these are less used. We have to remember that it's minus cotangent cosecant x is the derivative, and then times dx is du. Right? So there's the substitution for this one. And that might be hard to guess as a substitution, right? So we just memorize that it works for this. And you're thinking of this cotangent to the first, cosecant to the -2 is still an even power, so you can make this substitution. All right, so let's see. We've got to pull out the du, I'm going to rewrite this as minus the integral of 1 over cosecant cubed x times minus cotangent x cosecant x dx, right? That's the same integral. The minuses cancel. Cosecant over cosecant cubed is 1 over cosecant squared, and there's the cotangent. So that's the same integral, but what I've done is I've pulled out my du. This can substitute out for du. This is nothing more than u substitution. Again, it's just a clever choice. Quite a lot of these integral techniques we're going to see are just u substitution. I told you that's probably the favorite technique after the basic rules, but that's because there's these clever methods that people have found. Now, cosecant was the substitution, so this is actually u cubed. What I can now write this as is minus the integral, 1 over u cubed, and this is du. Right? I can integrate 1 over u cubed because after all, that's u to the -3. u to the minus 3 integrates as u to the minus 2 over minus 2, right? And then I've got the minus out front, just by the power rule, plus an arbitrary constant, gives us plus 1/2 1 over u squared plus a constant. Well, let's see. U is cotangent, and so I can write this as 1 over 2 cotangent squared plus a constant. But it might be easier to remember that cotangent is 1 over tangent, so we could also write this as 1/2 tangent squared x plus a constant would be even easier. But there's a nice example of integral of cotangent to a power times cosecant to a power.
Are we gonna get like a reference sheet with the derivatives of like trig functions or some identities of these, or do we have to memorize all of that?
I want you to memorize them all. Yeah, there is a rule we'll do today that I don't expect you to memorize, but I'll tell you when I don't expect it. Unless I say you don't need to memorize this, you need to memorize them all. Yeah. In the long run, that's how you learn to recognize these tricks, as you see something that looks familiar, and so that's where the memorization is important. Thank you. Now I'll make one comment on those methods. Note, if the powers that be in the integral
Dr. Stapleton,
yeah,
at the end, why is u not cotangent? Or
I miswrote that, didn't I? Thank you. Yeah, u was cosecant, and I was thinking that, and then I messed it up right at the end. Yeah, this should have been cosecant squared, and then 1 over cosecant is sine. So I guess it should have been 1/2 sine squared. Okay, yeah, sorry about that. U should have been cosecant. All right, if the powers that be in the integrals don't fit these rules, you can, this is not actually a real easy technique, you can convert to one of the others. I won't finish the example, but I just wanted to point out something that this does come up once in a while. For instance, suppose I have this one, integral sine to the 4th times cosine to the 4th. What can I do with that? There's actually a number of ways to go with this, but you could conceivably write this as sine to the 4th over cosine to the 8th, cosine to the 4th, excuse me, times cosine to the 8th, right? And then you can write cosine to the 8th. You can write this one, sine to the 4th over cosine to the 4th, as tangent to the 4th. And write cosine to the 8th as 1 over secant to the 8th dx equals dot, dot, dot. But actually, this is pretty hard. But you can do it. There's another way you can do this, however. You could write this as the integral sine to the 4th, and then write cosine to the 4th. Well, let's see, cosine to the cosine squared is 1 minus sine squared. Squared. So you could write it like that and get it as a power of, get it in powers of sine only. Then there's a rule to do these powers of sine only that are even. And this rule works for powers of sine odd, but powers of sine odd, the rule for integral sine of power times sine to a power times cosine of a power is easier. So you really only want to use this rule for the even powers. Let's see, was that 4 I just did? I think 5 was the reduction formulas. And I told you I'd say when you don't need to memorize this, these are too long and too seldom used to want to memorize them. So I'll say on this one, don't memorize it. If you need it on the test, I'll give it to you. But you need to know these are here because you'll see them in textbooks. You say, where did they get that from? And I've liked the proof of this. It's kind of neat, but I think I'm going to skip it and just say see the book because it's a little long and not that illustrative. But integration by parts. Shows, and you'll watch here, I'll read it out of the book because I don't have this one memorized either, that you have rules like this. This one is just for powers of sine like we were just talking about. If you have the integral of sine of x to the nth power, right? Integration by parts, you can try it yourself, it's not too hard, derives this formula, that integral of sine. Let's see if I can find it again. There it is. By the way, there's a whole list of these rules at the end of section 7.2. If you're saying to yourself on the homework, which rule do I use? Just look at the end of the section. They summarize all these. It's really a nice presentation, and you get used to, you can look these things up. I think there's a great reference when you get out of this class. Keep this book, and then when you get stuck on one of these trig integrals, just go to the end of this section. You can look it up and remind yourself which technique applies here. It says sine to the nth power is equal to minus sine to the n minus 1 power times cosine all over n plus n minus 1 over n times the integral of sine n minus 2. So if I see a high odd power of sine, I'll just use that integral sine to a power times cosine of power rule. But if I see sine to a high power that's even, I'm kind of stuck with this one or using that half angle identity a whole bunch of times, which is another possibility. But see what this rule does is it says if you have sine to a certain power, you can reduce it to a integral of sine to 2 powers less. And if you apply that over and over, it's really fun to watch Simbo Lab do this. You give it sine to the 10th power here, and it does this 5 times and gives you this whole long string of trig functions. But this reduction formula you don't memorize. I won't start that one. But it can reduce your problem. For instance, I'll just do a real simple one. Suppose I had that integral sine to the 4th problem again, that it comes out of the last example I did. How do I integrate that? Oh, one way to do it. Actually, let's do 2 ways to do it. You could use your old rule and use the half angle identity and write this as equal to, and write sine squared as 1 minus cosine 2x over 2. That's sine squared and then squared. So you could do this formula from half angle identity. And then say, oh, this is 1/4, right? 1/2 squared. Integral of, by foiling the top, 1 minus 2 cosine 2x plus cosine squared 2x. And then this one needs another half angle identity. You want to substitute this one is 1 plus cosine 4x. over 2 by the half angle identity. And then you can integrate every term. So I'll put equals dot, dot, dot. I don't think I'll finish that. I just want you to recognize the technique. This is sort of telling you the cookbook without recipe without actually cooking the pie. And so that's one way to do it, is with the half angle formula. But now we have a reduction formula. We could apply that instead. Right? Or B, we can say that the integral of sine to the fourth of x is, according to this formula, is putting n equals 4. Right? N equals 4 in the reduction formula is minus sine cubed cosine over 4, right? N equals 4, n minus 1 equals 3, plus 3/4 integral sine squared. And now, how do you integrate sine squared? That's one of the reasons we memorize it. You can rewrite it as a half angle identity, 1 minus cosine 2x over 2, right? Cosine squared of a is 1 plus cosine 2a over 2. Sine squared a is 1 minus cosine 2a over 2. So you can substitute that in there and then integrate this one, and I'll just put equals dot, dot, dot. You can integrate each of these two terms, right? Integral cosine 2x is 1/2 sine 2x and so forth. Maybe I should finish it. Let's just finish this one just to make it clear. So one way is to use the half angle identity twice, but you can also use the reduction formula and the half angle identity once. And you notice that when you get very high powers of sine, like sine to the 10th, this reduction formula is better than using the half angle formula over and over. So you'll see some of these online calculators do it. So if I want to take 3/4 and the integral of 1 minus cosine 2x over 2, integral of 1/2 is 1/2 x. Integral of, and then the minus 1/2, integral of cosine 2x is sine 2x over 2, you recall. So I'm using here that the integral of cosine kx was 1 over k sine kx by the u substitution rule plus a constant. And then a constant times 3/4 is still an arbitrary constant, so I'll just put it out there. And that's how that one comes out, right? We can reduce that a little. Okay? So this is getting a whole lot of trig integrals that come up in practice taken care of. All right, so I think this is rule number 6 coming up here. I didn't get involved in this. I forget where I was counting before sometimes. Suppose I had to integrate now instead integrals of sine mx times cosine nx with respect to x. The rules we have so far were power of sine kx, cosine kx. They had to have the same argument, kx. These are different multiples of x. Now what am I going to do with this? This one, again, it's a trig identity. This whole section on trigonometric integrals reduces to applying trig identities and applying u substitutions. There's nothing more than that. So in some sense, there's no new math here. It's just a matter of memorizing the cookbook, right? Figuring out which kind of integral you have. For this kind of integral, what you do is use the following trig identities. I'm going to derive it here because I seem to be able to remember this better by deriving it than by memorizing the result. I recall that sine of a plus b, right, the sum formula for sine, I think we all remember that because we use it a lot in other classes, is sine cosine plus cosine sine, right? Remember that one? Then there's a difference formula for sine. Sine a minus b is sine cosine minus cosine sine. And now you recognize if you were to subtract the second one from the first one, right, take away this one, these two would cancel, right? This will go away with this. And I'll get on the right this one plus this one. And actually, instead of subtracting, let's subtract and divide by 2. So if I take this one minus this one over 2, then I'll get, maybe put it up at the top here, I'll get sine A plus B subtract, I'm sorry, not subtract, add sine A minus B all over 2. So this one plus this one over 2 should be, add these and divide by 2. Gives me on the right, when I add these cancel and I get 2 of these over 2, oh, that's just sine A cosine B, right? So by trig identities, added divided by 2, I'll get this result. But that's precisely what the integrand is here, right? It's a sine times a cosine. So this allows us to rewrite the integral as treating mx as a and nx as b, integral of 1/2. There's the 1/2. Sine of the sum of these, mx plus nx, plus the sine of the difference of these, sine mx minus nx. So this is the formula if you want to memorize it. I won't star that one. I'll say what you really want to memorize probably is this trick, add them and divide by 2. But if you prefer, memorize this one. These can both be integrated, right? You can integrate sine of a multiple of x. This is just a number times x, and this is just sine of a number times x. It's easy, right? So we can do a simple integral like that, where you have a sine of one multiple of x times cosine of a different multiple of x, using this trig identity right here. I'll just plug it straight in as though I memorized it. So here's the example. Suppose I wanted to integrate sine 2x times cosine x dx. There are other ways to do this, obviously. I mean, for instance, sine 2x, I could use a trig identity, 2 sine x cosine x, and then I have sine times cosine squared. I could use the other method. Maybe I'll make it a little tougher. Let's make it this way, sine 3x times cosine x. Now I don't have another trig identity, but on the test, if you see a better trig identity, go ahead and use it, right? Sine 3x is not a well-known trig identity. There is one for it, but it's not all that easy. Let's instead use this trick here. I can rewrite sine 3x cosine x using this, this method here as 1/2 sine of the sum of these two things, sine of 3x plus x, sum of the arguments, plus sine of the difference of the argument, sine of 3x minus x. How about that? All with respect to x. So the 1/2 comes out, and I just have to integrate sine 4x and sine 2x. Those are easy memorized formulas, right? Integral sine 4x is just minus cosine x over 4. So I have minus, well, that's right, 1/2 minus cosine 4x over 4. Integral sine 2x is minus cosine 2x over 2. Then there's a plus c on the end, right? So there it is. I can integrate sine 3x cosine x by nothing more than a little trig identity to make the integral easier to recognize what to do. That one look okay? I hope. Then I'll say part of this same technique is to say, well, similarly, if you have an integral of sine mx times sine nx, so it's both sines, what can I do with that? Or integral cosine of mx times cosine nx. What am I going to do? M and N don't have to be integers, by the way, if you think about this technique. It's just the common letter they use for these. for these integrals, use, and this, as you can see, these always work, right? I did the derivation there. You can use the sum and difference angles formulas for cosine, right? Cosine A minus B is cosine minus sine. And cosine of the sum, that formula that we memorize, is cosine. Oops, this was plus, sorry. Cosine A minus B is cosine plus sine. Cosine A plus B is cosine minus sine. And now you can add these and divide by 2 or subtract and divide by 2. If you add them and divide by 2, you've got cosine A minus B plus cosine A plus B all over 2, right? Then these two cancel, right? And you're left with 2 of these over 2 is just cosine A cosine B. So use that in the latter case, right? You just replace this with integral cosine mx plus nx plus cosine of the difference mx minus nx all over 2. And in the case of this one, well, if you were to take the first one and subtract the second one and divide by 2, you've got cosine A minus B minus cosine A plus B over 2 is cosine sine A sine B. So these sum and difference formulas tell you how to rewrite these integrals. This one now rewrites as cosine mx, let's leave a little more room, cosine mx minus nx minus cosine mx plus nx all over 2 integrated. There's that one. So you can replace this one with this one, which you can do. You have your formulas already. You can replace this one with this one, which you have formulas. So this is the trick here. I won't star it because I'm saying maybe you don't want to memorize it quite so complicated. But if you just remember your half angle or your sum and difference formulas, you can figure out these trig substitutions to make something easier. All right. Do you want to see one of those, or should I just leave that there? I'm not sure. All right, so there's one more technique that we can apply. All right, I think that's all I want to do out of that section then, except yeah, that'll work right there. Now, one application of these comes up in trig substitution. So these are trigonometric integrals that come up quite a lot. Try those and see if you have any problems for next time. And by the way, when the lecture's over here, I'm going to sign off, but I'll sign right back on. The timer goes off at 50 minutes. I'll sign right back on, and if anybody wants to ask some questions for a few minutes after the lecture, I'll stay there 5 minutes. And if you're on, then I'll just stay on and answer questions. But get on within 5 minutes, and I'll get back on. Or you can see me in my office hour an hour after class ends. I'll also be online. All right, so that's the end of that section, and now we want 7.3, which is on trig substitutions. One reason those integrals we just did involving trig functions come up so much is that there's lots of trig substitutions that lead to precisely those kinds of integrals. So we need to be able to do those, and in order to finish the integrals when we do these kind of things. And here's the rules for trig substitution. There's 3 of them. We'll just say for integrals containing a square root a squared minus x squared. These come up quite a lot in applications. Once again, it's just a clever u substitution. Who would ever guess to make this substitution? You don't see a function of a function. But if you let u x equal a sine theta, so substitute out x in favor of theta, a new variable, and then corresponding dx is a cosine theta d theta. Makes an integral that's often something you can do. All right, so that'll be the first trick, and then there's some other tricks for square root x squared minus a squared and square root x squared plus a squared that we'll do besides that. But these tend to lead to precisely the kind of integrals we just had. All right. So here's an example. Suppose I wanted to just do this very straightforward integral, square root of 1 minus x squared with respect to x. What in the world could that be? It doesn't look so complicated, and yet what a mess, right? How can I evaluate that integral? The trick is to do this. You recognize it's got a square root a squared minus x squared with a equal 1 in the trick, and you just try that substitution. You let x equal a 1 times sine theta. And actually, it turns out x equals a cosine theta works just as well if you like cosine better than sine. This it works just as well. You can use either sine or cosine. If I make that substitution, which is just a clever choice, I told you that big integral of book of integrals that I have, a lot of that is just clever substitutions people thought of for really difficult integrals. So you make that substitution, then dx is the derivative of this d theta is cosine theta d theta, right? So I need to make this substitution. And so I just go up there and substitute, right? Dx gets replaced with cosine theta d theta. And then what do I replace square root 1 minus x squared with, I wonder? Well, you can figure it out because this is actually square root 1 minus x squared is square root 1 minus sine squared theta is cosine theta. When you're in quadrant 1 at least, minus cosine theta if you're in a quadrant where cosine is negative. But that's the trick. And so you can replace this square root with cosine theta. And I'm going to leave a little space here. And this just becomes integral of cosine squared theta d theta, precisely the kind of integral we've just been doing. So these integrals with square roots on them that come up quite often lead to these integrals with powers of sine and cosine quite often. And then that means I can, on the next exam, ask you just one question and make you do both techniques. Isn't that a good question for the test then? So you might get something with these square roots in them. I always like to put one of those in so I can test both techniques. Just a heads up ahead of time. How do I integrate cosine squared? That's one of the ones we memorized. We can rewrite this as integral 1 plus cosine 2 theta all over 2 by the half angle identity. Integral of 1/2 is theta. And integral of 1/2 cosine 2 theta is 1/2 times sine 2 theta over 2 is the integral cosine 2 theta. And we got plus a c in the end. Now, I want to point out one more thing. This takes care of it in terms of theta. You now got to put it in terms of x. So if x is sine theta, we infer that theta must be arc sine x. So this is actually 1/2 arc sine x plus 1/4. Wonder what sine of 2 theta is, right? Well, you can use, actually, let's write one. Yeah, all right. Sine, the double angle identity for sine, and say, oh, that's just 2 So the 1/4 comes from 1/2 times 1/2, and then sine 2 theta becomes 2 sine theta cosine theta by the double angle identity. You thought you'd never use your trig identities probably, right? But here they are, used quite a lot. Let me make this clear. It's not good to run these together, is it? There we go. So it's 1/2 sine theta cosine theta is what that multiplies out to, plus a constant. Now, what do we do with all this stuff? What is cosine theta? Wait a minute. Well, cosine theta, we let x equals sine theta. Cosine theta is actually square root 1 minus x squared. This gets kind of complicated. What's actually kind of nice on these figures to do is actually draw a right triangle, and sometimes this will actually help you to do this faster. And you'll see on the later problems, I'm going to pretty much always draw the right triangle. I don't need it for this very simple example, but for the longer ones, I will prefer it. You don't need it absolutely. What you do when you make this substitution is always also draw this triangle where x is equal to sine theta. How can I make x equal sine theta? Well, if I put theta as this angle, I could put x over here and 1 over here, and then here's a triangle where x over 1 is equal to sine theta, the very substitution I made. Now, what do I need for the last side in the triangle? I can use the Pythagorean theorem and say by the Pythagorean theorem, this is hypotenuse squared minus leg squared, so that this squared plus this squared equals 1, right? I get this by the Pythagorean theorem. So often what helps you to make these substitutions a little easier is to draw this triangle. Like I say, we don't absolutely need it on this one. And now from this triangle, you notice that x equals sine theta, this over this, but also this over this, square root 1 minus x squared becomes cosine theta. And so that falls right out, and sometimes it's a little easier to make this triangle. And you can make other trig functions, like if you get a secant in your answer, you can say, oh, that's this over this, 1 over the square root. Or the tangent, that's this over this. And so sometimes you have other trig functions to substitute, and this makes it a little easier. All right, so now I have this I need to substitute back for. Let me get rid of the integral. Let's write it over here. So this is equal to 1/2 arc sine x plus 1/2. 1/4 times 2 is 1/2. Sine theta cosine theta. Sine theta is x. Cosine theta is the square root. So it's x square root 1 minus x squared plus c. So there's my evaluation of this integral. And the nice thing is you can always check this right before you submit your homework. Go in online and try one of those integral calculators. Or you can take the derivative of this to see that you get back square root 1 minus x squared. All right. So there's the first trick. When you have a square root a squared minus x squared, you can make a substitution x equals a sine theta. So the next trick, we'll have to finish this next time. Second point in this section is that for integrals containing square root a squared plus x squared, let u equal a tangent theta. So these rules are pretty easy to memorize, right? If you see one of these square roots with squares in it, you're going to make a trig substitution. Sorry, not u, x. And you make a trig substitution, x equals a sine theta in the other case, x equals a tangent theta in this case, and next time we'll get x equals a secant theta in the third case. And actually, x equals a cotangent theta works just as well as tangent if you prefer cotangent to tangent for some reason. So let's try this one. Suppose I had the integral dx over x squared square root x squared plus 4. What am I going to do with that? Right? It looks nasty. It looks awful. But with this substitution, it clears up nicely. Again, what you really want to do is draw the triangle. Will sometimes shorten your work. You don't need the triangle, but it does help. if I put theta as one angle in a right triangle, and here I have x squared plus a squared, just written in the opposite order. So if this is a squared equals 4, I want to choose a equals 2. Right? So I'm going to make the substitution x equals 2 tangent theta. All right? Now, if x equals 2 tangent theta, that tells me that tangent theta is x over 2. And I can draw a nice triangle. I can put x here and 2 here. Now, tangent theta is opposite over adjacent is x over 2. The hypotenuse by the Pythagorean theorem is the root sum square of those. Square root of x squared plus 2 squared. All right? Oh, that's the very square root I need. And it always comes out that way, right? If you make the right substitution, one of the sides will give you the square root that you need. But now I can figure out everything I need out of this triangle when I evaluate the integral, and it's a little easier. So what am I going to do? I look at the triangle and I say, I need to substitute the square root out. How do I do that? Well, I notice from the triangle that this over this, square root x squared plus 4 over 2 is hypotenuse over adjacent is secant theta, which tells me that the square root that I see, square root x squared plus 4, can be replaced in the integral by 2 secant theta. So I'll go up here and replace that with 2 secant theta. X I can replace with 2 tangent theta. And then also I need dx. dx, if x is 2 tangent theta, remember derivative tangent is secant squared, so dx is 2 secant squared theta d theta. So I put all those things in. I replace this with 2 secant squared theta d theta. So the integral becomes this, 2 secant squared theta d theta is dx. And then x squared becomes 2 tangent theta squared. X squared becomes 2 tangent theta squared. And the square root of x squared plus 4 becomes 2 secant theta. Well, nicely, these 2's can cancel, and one of the secants can cancel. About out of time, so I'll have to pick this up just a little bit. This becomes integral of secant theta over tangent squared theta times a half d theta. Well, this is a power of secant times a power of tangent, the very integral we were just doing. So what do we see? We see the tangent of power of tangent is even, power of secant is odd. Oh, unfortunately, my trick doesn't work for secant and tangent. But remember, if these are the wrong powers, you can make a different tact at this. Replace secant with 1 over cosine. Replace tangent with sine squared over cosine squared. And now you'll get an integral that has the right powers for sine and cosine, right? This will now have the integral of 1/2, and then this is cosine squared over cosine is cosine over sine squared. And now the power of cosine is odd. You can substitute u equals sine theta by our other trick because it's an odd power of cosine, even power of sine. And I'll leave it there. You can now, that triangle, after you